and welcome. I am Dr. Pauline Fu. In this video, I will go over some questions about regression pitfalls. So the first question, it is a study published on the Professional Geographer about urban and rural counties in the western United States. There are 6 independent variables: total county population x1, population density x2, population concentration x3, population growth x4, proportion of county in land, proportion of county land in farms, 5-year change in agricultural land base. So those 6 independent variables are used to model the urban-rural rating of the county. Prior to running the multiple regression analysis, the researchers were concerned about possible multicollinearity in this data. The correlation matrix is presented here. So this is the correlation matrix. This table, okay, correlation matrix between all pairs of independent variables. Question A, based on correlation matrix, is there any evidence of the extreme multicollinearities? And question B, refer to the multiple regression results in the table. There is a results for multiple regression. This is the results. Okay, multiple regression results. Based on these results, is there any evidence of extreme multicollinearity? Okay, that is the question. So let's answer the first question first. So just try to adjust my computer. Okay. So the first question is based on correlation table, this table here, for every pair of independent variables. Okay. And the question asks you, is there any multicollinearity exist based on this table? So now let's examine this table. Okay. So for example, the correlation, actually there is a data correlation. So this column, if I get rid of this column here, because okay. And then this data, let me see here. So I should move this, shift this data. So I'll try to undo it and manually adjust it. So the result should be, this is x1 and this is x2, x3, x4, and x5. And then delete this one here. So this is the correlation. Okay, correlation. Double check. X2 visual. Yeah, that is correct. So this 0.2 means the correlation between X2 and X1 is 0.2. Okay, 0.2. And this 0.43, the correlation between X3 and X2 is 0.43. Okay. So let's randomly pick up another number. So this number here represents the correlation between X1 and X5 is negative 0.16. Okay. And if you have correlation greater than 0.5 or smaller than negative 0.5, we may consider there is a correlation between those two variables. But here in this table, we do not have any data that is greater than 0.5 or smaller than negative 0.5. So we conclude there is no correlation among these 6 variables. Okay. So the final answer to question A, no correlation. Okay, no correlation. Now, let's look at the regression result. This is the regression result. Okay, you have a beta estimate for all 6 variables. You also have the p-value for all 6 variables. And the overall model, this is not R2, this is R square. R square 0.44, adjusted R square 0.43, test statistic for F 32.47, p-value for F 0.001. Okay, so based on this result, the question asks you, is there evidence of multicollinearity? Okay, so let's look at this result. Okay, from the p-value, okay, from the p-value, looks like we have X1 is significant. Okay, and X3 is significant. Significant means the p-value smaller than alpha. Suppose alpha 0.05. Okay, so this one is significant. P-value smaller than 0.05. Okay, so there are 3 significant X. Okay, 3 significant X. Because their p-value smaller than alpha. So our conclusion, there is no evidence to show that there is multicollinearities. Okay, because we have 3 significant X value. Okay, and the overall model based on this p-value is significant. Okay, means some X contribute to the variable Y. So this is this question. So next question is about personality and aggressive behavior. So again, this is the research study published at Psychological Bulletin. Okay. This study reported that the Lincoln personality and aggressive behavior, 4 of the variables mentioned in the study were aggressive behavior, irritability, trait anger, and narcissism. Pairwise correlations for these 4 variables are given below. So those are the correlation pairwise among those 4 variables. Now, suppose aggressive behavior is the dependent variable, means aggressive behavior is Y. Okay, so aggressive behavior is Y. The question asks you, is the dependent is there evidence of extreme multicollinearity? So that is the question. Okay. So if aggressive behavior is Y, I just want to use some annotation. So if aggressive behavior is Y, and you have Y, the relationship between Y and irritability 0.77, Y and trait anger 0.47, Y and narcissism 0.5. Looks like they all have correlation. That is good because these three variables are X, irritability, trait anger, narcissism, and this is Y. Okay, you hope there is a strong relationship between X and Y. Okay, so there is no evidence of multicollinearity. Okay, so if you examine the relationship among X, irritability, trait anger, so irritability, trait anger, those are the X. This one a little bit greater than 0.5, but other than this number, the other variables are not correlated. Okay, so overall, there is no multicollinearity, no evidence of extreme multicollinearity. Okay, although some variable, irritability and trait anger has a little bit correlation, but overall, no. So this is this question. Now, next, suppose, I'll use another color. Suppose narcissism is a dependent variable. So this time, narcissism is Y. Okay. Narcissism is Y. The question is there evidence of extreme multicollinearity? Okay. So this time, narcissism is Y. So I'm going to narcissism. So this narcissism is Y, narcissism is Y, narcissism is Y. I'm going to use the box. Narcissism, narcissism, and narcissism. So the relationship, this is Y, this is Y, and Y. Y here. So, and aggressive behavior becomes X, okay? So this is fine, X and Y 0.5. Another X is irritability, 0.16, that is okay. And another X, trait anger, between trait anger and narcissism, 0.13. So those are Y, the correlation between Y and X, 3X. And now let's look at the correlation among those 3X. So we need to see the first pair is irritability. Irritability and trait. Irritability and trait, that is 0.57, caused a little bit of concern. And then we think about irritability and aggressive behavior. Irritability, aggressive behavior. This is 0.77. Hey, my doggy. Okay, sorry for my little doggy. He wants to get into the house. So another variable is we are now exploring if there are some correlation among 3X. Okay, So now I'm going to look at aggressive behavior is X, irritability is X, that is 0.77. Okay, 0.77. It is above 0.5, so caused a concern about possible multicollinearity. Okay, so that is anything else? Aggressive, between aggressive and trait, it is 0.48. It is not a concern. Okay, not a concern. So this one. So remember, when you consider narcissism as Y, we have the evidence of multicollinearity because irritability is an X, trait anger is also an X. Those two X has correlation 0.57. Aggressive behavior is X, irritability is X. Those two variables has a correlation 0.77. So overall, there is a correlation. So this is a yes. Okay. So in summary, this example, when you consider multicollinearity, you have to pick a variable as Y. Once you pick a variable as Y, you examine the correlation among those X. If there is a correlation, then multicollinearity may exist. Okay. All right, so this is this question. Next. Steam processing of peat. A bioengineer wants to model the amount, that is the Y, the amount of carbohydrate solubilized during steam processing of peat as a function of temperature, X1, exposure time, X2, and pH value, X3, data collected for each of 15 peat samples were used to fit the model. So where is the model? This is the model here. EY equal to, EY equal to beta 0 plus beta 1 X1 plus beta 2 X2 plus beta 3 X3. Okay, so this is the model. A summary of regression results is this: Y hat equal to negative 3000 plus 3.2 X1 minus 0.4 X2 minus 1.1 X3. So based on this regression, we know beta 0 is negative 3000, beta 1 is positive 3.2, beta 2 negative 0.4, and beta 3 negative 1.1. Okay. And the regression result also gave us the R square, not R2, R square, 0.93. This is a high R square. And then give us the standard error of the coefficient. So the standard error for beta 1 is 2.4. The standard error for beta 2, 0.6, etc. And also give us the correlation. So this R12 means the correlation between X1 and X2 is 0.92. And the correlation between X1 and X3, 0.87, etc. Okay. So now, based on these results, the bioengineering concludes that none of these three independent variables is a useful predictor of the Y. Do you agree with this statement? Explain. Okay. So that is the question. Okay. So let's look at the correlation. First, the correlation between x1 and x2, 0.92, that is very high, okay? If it is greater than 0.5, there is a correlation, a chance of correlation. This is 0.92, very high correlation between variable x1 and x2. Again, higher correlation between x1 and x3, 0.87, and high correlation between x2 and x3. So all those three variables are highly correlated. Okay, so that's why there is a multicollinearity, strong evidence of multicollinearity. And also we have the high value for R squared. This supports our claim that there is a high evidence of collinearity. Okay, this is on one hand. On another hand, if you calculate the test statistic for variable 1 for x1, remember what is test statistic? It is beta 1 divided by standard error of beta 1. And beta 1 is given 3.2. Standard error for beta 1 is 2.4. And this result would give you 1.33. So similarly, you can calculate the test statistic for x2. So it is beta 2 over standard error of beta 2. And beta 2, 0.6. Standard error for beta 2. A standard error for beta 2 is 0.6. Beta 2 is a negative 0.4. Okay. Negative 0.4. And the result of this is negative 0.67. Okay. And next test statistic for x3 is beta 3 over standard error for beta 3. Beta 3, negative 1.1. Standard error for beta 3, 0.8. So the result you get is negative 1.375. Okay. So that is the test statistic. Once you have test statistic, you get critical value for t. Critical value for t. Suppose alpha is 0.05, and usually it is a two-tailed test. Okay, so when alpha 0.05, half alpha 0.025. Okay, and degree of freedom equal to sample size minus number of variable for x plus 1. Okay, so sample size is 15. And how many x? We have 3x. So degree of freedom equal to 11. And once you have degree of freedom, you have alpha. You can find the critical value. How? The simple way you can use Excel. Excel is based on area to the left. So you want to find this critical value. Okay, and the area to the left, this area is 0.975. 0.975. Why? Because this little tail is half alpha. This is half alpha, or 0.025. Okay, so you get the area to the left of the critical value. This point is a critical value, T, critical value. So the question is, how do I find this critical value? You go to Excel. So I will type in here. Okay. You type in equal T dot INV, means critical value, probability 0.975, comma, degree of freedom 11. Okay. So that is the formula. So you get 2.201 as critical value. Okay. So this value, how do I get it? Excel, you type in equal T dot INV. T dot INV. The parameter you type in 0.975, comma, degree of freedom 11. Okay. And then degree of freedom 11, you will get critical value 2.201. Okay, 2.201 is the critical value. And now compare critical value with your test statistic. All of these are not in the rejection region. All the test statistics not in the rejection region. Remember what is the rejection region? Critical value decide rejection region. So this is rejection region, and this is rejection region. This point is 2.201, and this point is negative 2.201. Okay, so none of this in the rejection region, all these test statistics. So all these three variables are not significant. Okay, all x1, x2, x3 are not significant. Okay. So there is a strong or extreme evidence of multicollinearity in this situation. Okay, because of that, we cannot conclude none are useful, because maybe one or two of them are useful. If you put all three of them together, there are multicollinearity occurred. Okay, so the final conclusion, do you agree, disagree? Okay, disagree because the multicollinearity. So this is this question. Last question. We need to use SPSS. This is an investigation of a meat processing plant. A particular meat processing plant slaughters, steers, and cuts and wraps the beef for its customers. Suppose a complaint has been filed with the Food and Drug Administration against the processing plant. The complaint alleges that the consumer does not get all the beef from the steer he purchased. In particular, one consumer purchased 300-pound steer, but received only 150 pounds of cut and wrapped beef. To settle the complaint, the FDA collected data on the live weights and dressed weights of the 9 steers processed by a reputable meat processing plant, not the firm in question. The results are listed in this table. Okay, so we have variable X, that is the live weight. We have dressed weight, that is the Y. Okay. Now the question asks you to fit the model to the data. Fit the model to the data. So you are given the raw data. How do you fit the model to the data? That is one question. And then construct 95% prediction interval. Okay. And then answer the question whether the 150 pounds is a reasonable amount to receive from 300 pound steel. Okay, so there are 3 questions. Let's answer question 1, fit the model to the data. Okay, so this question, I will use SPSS to do it. So where's my SPSS? It's not here. I cannot try to locate my SPSS. Here. So this is my SPSS. So I'm going to delete unnecessary variables. I just did some exercise. I'm going to delete all of these variables. Okay. And then this is the original data. Okay, this is the original data. And which one is X, which one is Y? This live weight is X. Maybe I will clearly label. This is X, and this is Y. Okay. And then I go to data view. So now fit the model. You go to analyze, regression, linear. Beautiful sound today. After that, you put dependent. No, that is not correct. Dependent means Y, so you put Y here. Independent is X. Okay. And then question 2 also asks you to produce a prediction interval. So you click Save button. Save button. Under the prediction intervals, you can click maybe mean and individual. And it is 95%. So we do 2 questions at the same time. Okay. After that, you click continue. And then click OK button. Okay. So now this is the result of multiple regression. Not multiple. Okay, it is just a single linear regression because we only have one variable X. Okay, one variable X. And to fit the model, you just concerned about the constant and the coefficient here, these 2 numbers. But you need to make sure this model is significant. How do you know the model is significant? You go to ANOVA table, look at the p-value here, p-value or the sig value. The sig value is smaller than 0.05, the model is significant. Okay, so I may want to copy this screen to OneNote so that I can analyze. Okay. So I'm just adjusting my computer. It is all right. So I have this result. And then I can make annotation. So the question asked me to fit the model, but before I fit the model, I want to make sure the model is significant. So this p-value smaller than alpha. Therefore, I conclude the model is significant. And then I can write down the model. And this is beta 0, 5.7. Beta 1 is 0.626. Okay, so the model is EY equal to beta 0 plus beta 1x. Beta 0 is 5.711 plus beta 1x. Beta 1 is 0.626 and then times x. That is the model to fit the data. Okay. At the same time, I also got the prediction interval. Okay. So this is the mean is the prediction interval. Okay. So the value is here. Lower bound, upper bound. This is the individual confidence interval for individual values. Lower bound, upper bound. Okay. So for last question. If you can, where's my OneNote? Last question. Whether this one is a reasonable amount to receive a 300-pound steel. Okay, so basically you go to, so when x equal to 300, can you use the model? The answer is no, because 300 is outside this range. Whenever you make prediction, you got to make sure the value is inside this range. So the smallest value in this data set is what? 340. Okay, 340. And the maximum value is 460. 300 is not in the data range. So you cannot make prediction because we do not know what happened outside this range. It could be linear, could be quadratic, could be polynomial, could be something else. Okay. All we can say is when the data between 340 and 460, we can use this simple linear model to fit the data. All right. So in summary, this lecture or video addressed some problems with the multiple regressions, such as to predict a value outside the data range, such as the multicollinearities. Okay, and also be careful, make the cause. If the data is from observational data, you cannot say X cause Y. You can only say X has some relationship with Y. To have the conclusion that X cause Y, you have to use a designed experiment. Okay. All right. So that's all for this lecture. Thank you so much for your time. I'll see you next time.